Namaste dosto. Imagine you're playing a game where you want to guess the color of a card, but you're told some extra info, like the card is from the red suits. How does this new knowledge change your chance of picking a specific card? That's the heart of conditional probability, which we'll explore today as the foundation for Bayes' theorem. Conditional probability helps us figure out how likely an event A will happen if event B has already occurred. We write it as P of a given B, or simply P of a vertical bar B. It's like saying, given that I know B has happened, what is the chance of A? Mathematically, conditional probability is defined by this formula. P of a given B equals P of A and B together divided by P of B. But remember, P of B must be greater than 0, otherwise the division can't happen. So, it looks like this. Slow, P of a given B equals P of A intersect B over P of B. This concept is essential because it captures the idea that events can be interconnected. Event A might depend on event B. And conditional probability is the backbone for many advanced tools in probability, including Bayes' theorem, which lets us update our beliefs based on new data. You'll find this idea popping up in all sorts of real-life uses. From medical testing where we assess the chance of having a disease given a test result, to decision-making in business, and even in machine learning models that predict outcomes based on data patterns. Also, imagine a Venn diagram showing two overlapping circles, A and B. The overlapping shaded part represents A intersection B, and the whole of B is the base for our calculation. Keep this picture in your mind as a simple way to understand conditional probability visually. Shabash. We now have a solid base to move forward. Let's move ahead. We learned how to calculate P of a given B. But what if we want to do the reverse? That's where Bayes' theorem comes in. It allows us to find P of B sub I given A, flipping the condition around. This means we look for the probability of a hypothesis B sub I being true once we have evidence A. Why is this useful? Sometimes directly finding P of B sub I given A is tricky. But we might already know P of a given B sub I, the likelihood of seeing evidence A if B sub I were true. Bayes' theorem helps us use that known likelihood to find the probability we really want. Imagine you divide your whole range of options into several separate, mutually exclusive events like B1, B2, all the way to Bn. These events cover the entire sample space without overlap, and our evidence A can come from any of these. This relies on something called the law of total probability, which sums up the chances across all these possibilities. Bayes' theorem is expressed mathematically as follows. P of B sub I given A equals P of B sub I times P of a given B sub I, divided by the sum from j equals 1 to n of P of B sub j times P of a given B sub j. Let me say that again slowly. P of B sub I given A equals P of B sub I multiplied by P of a given B sub I, all over the sum of P of B sub j multiplied by P of a given B sub j as j runs from 1 to n. This formula lets you update your beliefs or probabilities of hypotheses by incorporating new evidence, which is super helpful in fields like diagnostics, finance, and machine learning. To picture this, think of a flowchart or a funnel where prior probabilities get updated by evidence to become posterior probabilities. The updated chances after seeing the new data. Isn't it amazing how math helps us reverse conditions logically? Arey vah! Next, let's state Bayes' theorem formally with all the math clearly lined up. Suppose you have events B1, B2, up to Bn, which form a partition of the sample space. That means each pair of these events does not overlap. In math, we say B sub I intersect B sub j is empty when I is not equal to j. And together, their union covers the entire sample space. Now, pick any event A for which the probability P of A is greater than 0, so it's possible that A happens. Bayes' theorem tells us the following. P of B sub I given A equals P of B sub I times P of a given B sub I, divided by the sum of P of B1 times P of a given B1 plus P of B2 times P of a given B2 plus and so on, all the way up to P of B sub n times P of a given B sub n. Let me repeat this carefully. P of B sub I given A equals the numerator P of B sub I multiplied by P of a given B sub I, divided by the denominator, which is the sum from 1 to n of p of b sub k times p of a given b sub k. In a sense, this theorem combines your initial belief about b sub I, called the prior probability p of b sub I, with the likelihood of seeing a when b sub I is true, given by p of a given b sub I. The output is the updated belief after considering the evidence. That's p of b sub I given A, also known as the posterior probability. Picture a tree diagram now, where one set of branches represents the events b1 through bn, your hypotheses. And from each branch, further branches represent the possible outcomes of event given those hypotheses. The tree ends with the posterior probabilities computed by Bayes' formula. Excellent. This clear structure lets us apply Bayes' theorem systematically. Before diving into Bayes' theorem applications, there's a crucial step, finding P of A itself, the total probability of evidence. And that comes from the law of total probability. When you split your sample space into the partition events B1 through Bn, all with positive probabilities, the total probability of A is the sum over all I from 1 to n of P of B sub I times P of a given B sub I. Let me state it slowly. P of A equals the sum from I equals 1 to n of P of B sub I multiplied by P of a given B sub I. This formula measures the chance of event happening at all by considering all the different ways it can arise through the various B sub I events. Why is this important? In Bayes' theorem, this total probability forms the denominator. It ensures the posterior probabilities sum correctly and provides the baseline of evidence likelihood before updates. Shabash. Time to see Bayes' theorem in action with a practical example, a medical test. Suppose a certain disease affects 1% of the population. That's P of D equals 0.01, where D stands for having the disease, and P of not D, written as D prime, equals 0.99. The medical test for this disease is 99% accurate for both positive and negative results. This means if a person has the disease, the test shows positive 99% of the time, and if they don't, it correctly shows negative 99% of the time. We want to find the probability that a person actually has the disease given that their test came back positive. In probability notation, we want P of D given plus, where plus means a positive test result. By Bayes' theorem, this is P of D given plus equals the probability of disease times probability of positive given disease, divided by probability of disease times probability of positive given disease plus probability of no disease times probability of positive given no disease. Let me say this slowly. P of D given plus equals P of D times P of plus given D, divided by P of D times P of plus given D plus P of D prime times P of plus given D prime. Now, plug in the numbers. P of D equals 0.01, P of D prime equals 0.99, P of plus given D equals 0.99, and P of plus given D prime equals 0.01. Calculate the numerator. 0.01 times 0.99 equals 0.0099. The denominator is 0.0099 plus 0.99 times 0.01, which is again 0.0099. So the denominator is 0.0099 plus 0.0099 equals 0.0198. Dividing numerator by denominator. 0.0099 divided by 0.0198 equals 0.5. So even with a positive test, the probability that the person has the disease is only 50%. This might surprise you, but it's due to the low base rate of disease in the population, creating a lot of false positives relative to true positives. Arey wah! Always remember, positive test results don't always guarantee disease, which makes Bayes' theorem vital for medical decision making. Let's tackle another example with 3 boxes, each containing balls of different colors. Imagine you choose a box randomly, then pick one ball from it and find that it's red. What is the probability that this red ball came from a specific box? That's exactly what Bayes' theorem helps us find, the posterior probability of the source box given the red ball. Let's call the events B1, B2, and B3 for choosing each of the 3 boxes. Let event be drawing a red ball. We want to find P of B1 given A, For example, since the box selection is random, the prior probabilities P of B 1, 2, and 3 are each 1/3. Next, we calculate the likelihood of drawing a red ball from each box, denoted as P of a given B sub I, based on the ball composition inside each box. Using the law of total probability, the total probability of drawing a red ball is P of A equals 1/3 times P of a given B 1 plus 1/3 times P of a given B 2 plus 1/3 times P of a given B 3. Let me repeat that. P of A equals 1/3 multiplied by P of a given B 1 plus 1/3 multiplied by P of a given B 2 plus 1/3 multiplied by P of a given B 3. Finally, apply Bayes' theorem to find P of B 1 given A. P of B 1 given A equals 1/3 times P of a given B 1 divided by P of A. Substitute actual numbers from the ball counts to compute this clearly. The result gives us our updated confidence that the chosen red ball came from box 1, refined by how likely each box is to produce red balls. Excellent. Posterior probabilities like these show how Bayes' theorem updates beliefs based on observed data. To wrap up, let's summarize the important formulas and ideas we covered today. First, conditional probability. P of a given B equals P of A and B together divided by P of B, assuming P of B is greater than 0. Next, the law of total probability. P of A equals the sum from I equals 1 to n of P of B sub I times P of a given B sub I. And finally, Bayes' theorem itself. P of B sub I given A equals P of B sub I times P of a given B sub I divided by the sum over J of P of B sub J times P of a given B sub J. Key ideas to remember are that Bayes' theorem reverses the direction of conditional probability, letting us update prior beliefs using new evidence. It is central to decision-making and prediction in many fields. Its accuracy relies heavily on how good our prior probabilities and likelihood estimates are. That's why collecting reliable data is as important as the math itself. Bayes' theorem is widely used in medical diagnostics, spam filtering in your email, predictive models, and classification tasks in machine learning. Soch ke dekho. Behind many smart decisions, this elegant theorem quietly works in the background. Keep practicing these concepts and formulas, and you'll see how powerful probability can be. Shabash.